Well, hello, I'm Amanda Knutson, and I am going to demonstrate the Hall effect and how it can be used to activate a motor. This presentation is for Dr. Buckner's electromechanical systems class in summer of 2009. I also thought that this might be a good opportunity to teach our cameraman, go back out now, David, who is David Long, a little bit about electromechanics. He's a family friend and a neighbor of ours, and he will be entering high school shortly. So maybe you will end up having an interest in electromechanics.
I'm already in high school.
That doesn't matter. And I also have my daughter here. She's attached to my leg at the moment. What I've drawn on the board is a conductor with a magnetic field applied to it. You can see in the upwards pointing arrow B. So if you have it subjected to a magnetic field that is supplied with a current from a voltage source, then the magnetic field will exert a force on the charges which will separate them to either sides of the conductor. The buildup of charges on the sides balances the magnetic field influence, and that produces what's called Hall effect voltage. The equation for the Hall effect voltage was derived down below. So at equilibrium, the force due to the magnetic field is equal to your force due to your electric field, and that is equal to your Hall voltage times charge density divided by the width of the conductor. So from that you can solve for your Hall voltage as being the product of your current times the magnetic field. That's divided by your charge density, the electron charge, and the thickness of the conductor. So what's happening here is when you have a voltage source applied, then assuming that the number one magnet is the closest to the Hall effect sensor, which is the block with the X in it, then you have a signal that runs from your sensor up to your transistor, and that opens the current to go to your electromagnet, and when that current goes through the electromagnet, then it repels the permanent magnet number 3, and that gets the motor turning. When that happens, then your signal due to your permanent magnet number 1 stops from the sensor to your transistor until the number 2 permanent magnet lines up with the Hall sensor, in which that whole process will repeat again, and that's what gets the motor to turn, is that repetitive process. Here is the Hall effect motor, and I have it set up with 4.5 volts of supply voltage, and when I connect the leads, it gives intermittent results. I think it has something to do with the way that the Hall sensor was positioned and glued on. It was working fine before when I initially put it together, but when I glued down the Hall sensor is when it started getting intermittent results. So the motor goes back and forth but doesn't complete a turn. Anyway, here's what it looks like. So this could be due to finding a what is called a dead spot, which is a position where the rotor stops and can't really start again without a push, but it still doesn't complete and start running on its own. Now here is the motor with 6 volts applied as the source voltage. Can't really tell much difference between how it reacts with 4.5 volts versus the 6 volts, since it's not completely rotating and spinning on its own power. I've added the fan to the front because it makes it a little easier to see. Some other things that could be done if the motor actually turned on its own power, I could have measured the torque and compared the speed and torque with the different voltage settings, and I would plan to do that. So that is how this the Hall effect motor works. I think that if I were able to fix the problem with the intermittent spinning by probably adjusting the Hall sensor position, and I could even add a heat sink to dissipate the heat, and I could probably allow this to be connected for a little while and have the fan spinning and provide some entertainment for a 2-year-old for a little while anyway. That's it. If you have any questions, please email me. Thank you.